Dear viewers, welcome to my YouTube channel Electrical Passionate. Today I shall discuss about fault current calculation in details with example. Request you to watch the video till the end. Most of the faults on the power system lead to short circuit condition. When such a condition occurs, a heavy current called short circuit current flows through the equipment. Determination of this short circuit current under fault condition is an important matter to choice and design of apparatus and equipment like circuit breaker and relay. Today I shall limit my discussion to the fault current calculations due to symmetrical faults. Fault calculation, a crucial aspect of electrical system design and analysis, determines the current that flows during abnormal condition like short circuit and earth fault. These calculations are essential for the selection of protective relays and other equipment to ensure safety and reliability of electrical system. Fault calculations deal with determination of current and voltage for various fault conditions at different locations of the power system. Such calculations provide the necessary data for selection of circuit breaker and design of protective relay like relay coordination. The faults are classified as symmetrical faults and unsymmetrical faults. Symmetrical faults. These faults involve where the three phases are affected equally, such as three-phase short circuit LLL and three-phase short circuit without LLLG. Unsymmetrical fault. These faults involve where one or two phases are affected, like single line to ground SLG fault, line to line LL fault, line to ground LLG fault. Calculation of fault current depends on some laws, representation of electrical system by diagram, and on system parameters. Ohm's law, the law used to calculate fault current, stating the current I is equal to voltage V divided by resistance R, that is I equal to V by R. Impedance or reactance diagrams, a visual representation of the electrical system by one line diagram used to determine fault currents by considering the impedances or reactances of various components. Such fault can be solved on per phase basis. The system is represented by a single phase system considering phase and neutral. Percentage, per unit reactance and base kVA system. Method, used to standardize calculations, allowing for the comparison of different system parameters. Fault level calculation. It determines the fault current that can flow during a fault is expressed in fault MVA, megavolt amperes, or KA, kiloamperes. Example: to calculate fault MVA in a transformer, we can use the following formula. Fault MVA is equal to transformer rated MVA into 100 by percentage impedance. The symmetrical fault occurs when all three conductors of a three-phase line are affected equally into a short circuit condition. Fault current IA, IB and IC will be equal in magnitude with 120-degree displacement among them. Because balanced nature of fault, only one phase need to be considered in calculation. Since condition in other two phases will be similar. When a short circuit occurs at any point in a system, the short circuit current is limited by the impedance of the system up to the point of fault. If a fault occurs on the feeder at point F, see the picture, then the short circuit current from the generating station will have a value limited by the impedance of generator and transformer and the impedance of the line between generator and the fault point. The impedances of transformer, generator and reactor limiting the short circuit currents are largely reactive. Cable and lines are mostly resistive, but where the total reactance in calculation exceeds 3 times the resistance, the latter is usually neglected. The first step in fault calculation is normally to draw a single line diagram. In the diagram, the components of the system are usually drawn in the form of their symbol. A balanced three-phase system can be conveniently solved on single-phase basis. It can be represented by a single-phase system having one phase and a neutral. Percentage reactance. The reactance of generators, transformers, reactors, etc. is usually expressed in percentage reactance to permit rapid short circuit calculation. The percentage reactance of the circuit is defined as the percentage of total phase voltage dropped in the circuit when full load current is flown, that is, percentage reactance is equal to Ix into 100 by V, where I equal to full load current, V is equal to phase voltage, X is equal to reactance in ohm per phase. Alternatively, percentage reactance can be expressed as percentage reactance is equal to kVA into X divided by 10 into kV square, where X is equal to reactance in ohm. If X is only the reactance element in the circuit, then short circuit current is given by I short circuit ISC is equal to V by X is equal to I into 100 divided by percentage reactance. As we know, percentage reactance X is equal to Ix into 100 by V is equal to I by X by 100. For example, if the percentage reactance of an element is 15% and full load current is 60 amperes, then short circuit current will be 60 by 0.15 is equal to 400 ampere. Fault calculation normally begin with drawing single line diagram of the given system. Next, suitable kV and kVA bases are chosen for such voltage level. Thereafter, reactance diagram or positive sequence diagram network of the system is drawn. These are preliminary steps in fault calculations. Let us consider a three-phase transmission line have operating voltage 66 kV connected through 1000 kVA transformer with 5% reactance to a generating station bus having generator of 2500 kVA with 10% reactance represented by the single line diagram. Suppose a three-phase fault occurs at the HV side of the transformer at a point F. Now we have to calculate the fault current due to this fault. It is necessary to find the percentage reactances of all the elements on a common kVA rating. This common kVA rating is known as base kVA. The value of this base kVA may be equal to that of the largest element, equal to total plant capacity, any arbitrary value. But the value of base kVA does not affect the short circuit current. The conversion percentage reactance to base kVA can be done by using the formula percentage reactance at base kVA is equal to base kVA into percentage reactance at rated kVA divided by rated kVA. Thus, a 2500 kVA generator with 10% reactance will have a reactance is equal to 5000 into 10 divided by 2500 is equal to 20% at 5000 kVA base. Suppose we choose base kVA is equal to 2500 kVA. On this base kVA, the reactances of various elements in the system will be reactance of transformer will be is equal to 5 into 2500 divided by 1000 is equal to 12.5%. Reactance of generator will be equal to 10 into 2500 divided by 2500 is equal to 5%. XAB, reactance between the ends A and B is equal to 5 plus 10 is equal to 15%. The full load current of the circuit to 2500 kVA base at 66 kV side, I equal to 2500 into 1000 divided by root 3 into 66 into 1000 is equal to 1.87 ampere. Therefore, short circuit current ISC is equal to I by 15% is equal to 1.87 divided by 0.15 is equal to 97.2 amperes. Now, it will be shown for any value of base kVA, short circuit current remains same. Suppose we now choose base kVA is equal to 5000 kVA. On this base kVA, the reactances of various elements in the system will be reactance of transformer will be equal to 5 into 5000 divided by 1000 is equal to 25%. Reactance of generator will be equal to 10 into 5000 divided by 2500 is equal to 20%. Therefore, XAB equal to 20 plus 25 is equal to 45%. The full load current of the circuit to 5000 kVA base at 66 kV side is equal to, that is I equal to 5000 into 1000 divided by root 3 into 66 into 1000 is equal to 43.74 ampere. Therefore, short circuit current ISC is equal to I divided by 45% is equal to 43.73 divided by 0.45 is equal to 97.2 amperes. So, the same fault current is obtained by using different base kVA. The MVA in case of three-phase fault would be equal to fault MVA F equal to root 3 V into IF. IF is equal to fault current in kiloamps 90 degree lag is equal to 97.2 ampere is equal to 0.0972 kiloamps angle minus 90 degree, where V is equal to phase to phase voltage in kVA RMS is equal to 66 kV. So, fault MVA F equal to root 3 into V into IF is equal to root 3 into 66 into 0.0972 angle minus 90 degree is equal to 11.11 MVA angle minus 90 degree.